Hello everyone, I am Loïc Henriet, co-CEO at Pasqal. At Pasqal, we build quantum processors with neutral atoms, and I will tell you today about our journey from laboratory to making an industrial quantum processing unit for applications. Pasqal is a unique mix of science and engineering. Our mission is to engineer those devices and make them reliable, stable, industry grade. But we're actually coming from a legacy of very strong scientific excellence, and we're happy to be counting Professor Alain Aspect, Nobel Prize in Physics in 2022, as a co-founder of the company. What he likes to say is that when there are no fundamental limitations, engineers find a path. All the fundamental discoveries have already been made with neutral atoms, how to control them, entangle them, manipulate them, and now we are going into the engineering phase. In the first part of this presentation, I will describe how we managed to get where we are right now, how we went from a laboratory experiment to an integrated product ecosystem. Our flagship products are hardware products, the Orion generation of processors. What you are seeing on the screen is our first generation of processor, the Orion Alpha device, which is an industrial device that is plugged online through the cloud and can implement use cases for our clients and partners. A little bit about our technology. Maybe you were there yesterday during the special lecture from Professor Michel Lukin at Harvard. He described a bit what are the basic blocks of our technologies, neutral atoms. Our qubits are individual atoms that we control with laser lights. Everything happens in the vacuum chamber that you can see on the screen, where we have a very low pressure, corresponding to the pressure that you'd find at the surface of the moon. Using tightly focused laser beams, we can individually trap and control rubidium atoms, and those are our qubits. This technology has been developed over the past few decades in France at Institut d'Optique, also in the US, in Mark Safman's group and Michel Lukin's group, and also here in Korea at KAIST with Professor Ji-wook An, who was one of the pioneers in the early days of this technology. So our atoms are qubits, and we use laser light to encode quantum information on those qubits. The 0 and the 1 of our qubits, they correspond to distinct electronic levels of those atoms. And using light, we can induce transitions between those states. In terms of readout, we use a standard camera in order to distinguish the zeros and the ones at the end of the computations. Neutral atom quantum processing units are very powerful in the sense that they can implement various computing paradigms. You can use them for analog quantum computing and gate-based quantum computing. Analog quantum computing is when you're tuning the Hamiltonian of the system in time continuously to implement a quantum algorithm. This mode is very powerful and is already providing results that are beyond classical supercomputer capabilities. Of course, we can also implement gate-based quantum computing, where programming a quantum circuit with digital gates. In that framework, a quantum algorithm is broken down into a sequence of elementary gates that are modifying the system in time. On the right side of the image, you can see a benchmark that was carried out already a few years ago in Paris for a simulation of quantum matter, how a magnet would evolve when put at very low temperature. This can be done using an analog mode for the quantum processing units. What you can see on the left part of the image is that experiment and theory, state-of-the-art theory, and state-of-the-art numerical simulation agree on the one particular observable, which is the correlation function, which tells you how tiny magnets orient themselves with respect to one another when put at very low temperatures. So this works for a 10 by 10 array. You can still simulate the dynamics of the system, but when you go to 14 by 14 array, there is no way you can compute these dynamics using a classical supercomputer. The only way to get an answer for that particular problem to create an antiferromagnetic state of matter is using quantum processing units. An interesting figure is to try to understand what you would need to replicate this experiment on a gate-based quantum computer. And actually, you would need very large number of gates with very good fidelities. Typically 10 to the 6 gates with infidelities that are below 10 to the minus 6. Neutral atom technologies have gained a very strong momentum over the past few years. I'm showing here two important figures of merit to try to assess various technologies with respect to one another towards quantum error correction. On the left side, I'm showing the entangling state error. So the lower, the better. You really want that to be near zero with respect to time, the evolution of this metric for various technologies. So of course, ion traps were the first to be able to realize very efficient gates with high fidelities. Superconducting qubits caught up in the past decade and managed to have gate fidelities at the level of ion traps. And as you can see, neutral atoms have started far later, around 2010, but since a few years, we've been witnessing a very strong increase in gate fidelities. So this matrix is going very strongly down to zero, and we are at the level now of the other technologies with neutral atoms. Now, when it comes to number of qubits, neutral atoms are clearly in the lead. We have been able to control registers of several hundreds of qubits in the academic labs and also in startup companies. So with respect to time, you can see the number of qubits evolving and neutral atoms clearly advancing trapped ions and really at the level of superconducting qubits right now, with very strong prospects for even scaling even further. So with gate fidelities approaching 10 to the minus 3, qubit number moving towards more than 1,000, fault-tolerant quantum computing is getting closer, as was illustrated yesterday by Michel Lekenstock. At Pasqal, we are happy to be contributing to this increase in performances. You can see here a picture of some results that we have done in our lab at Pasqal in France, where we've been able to trap on a single shot more than 1,000 atoms, paving the way to large-scale quantum computing. On the right side, we've been playing with the shape of those atoms to rearrange them with 828 atoms selected. So I've told you about the technology, and now I will be focusing a little bit more about what makes Pasqal specific, what is our specificities in terms of company about our approach. Our approach is really to go strongly on engineering. As I said, what we need right now is higher stability, uptime, repeatability for those devices to really take this technology out of the lab and into the field so that practitioners can use them. So we've been working on improving modular design with sub-modules with well-defined interfaces at the hardware level. It's really beneficial. It provides stability, ease of use, and maintenance. And we can also continuously improve the capabilities of our devices while keeping the interfaces fixed. You can see two examples of subsystems that we've been developing internally at Pasqal for various features of the quantum processing units. This is quite key to be able to attain very high uptime. So right now, our Orion Alpha device, which is plugged on Azure Quantum Cloud, is able to be operational 90% of the time, 24/7, without human intervention when put in production period. So you really need to understand that this is hard to actually take something which is operating a few percent of the time in academic labs and make it an industrial product 90% of the time reliable where you can use it. As a sign of the stability of this device, I'm showing here a few examples of the client use cases and partner use cases that we've been implementing over the past few months on our Orion Alpha device. As you can see, they range from various fields and domains, like biochemistry, telecommunication networks optimizations, mission planning for satellites. And the algorithms that we can implement can fall in 4 main categories: graph machine learning, optimization, quantum materials, and also solving partial differential equations. And for more focus on our application, I invite you to go to Andreas Gentile's talk tomorrow. We will be talking about our applications at Pasqal. We're happy to have attained good results recently with major players in the global industry recognizing the momentum at Pasqal. On May 20th, we have signed an agreement with Saudi Aramco to install a quantum processor in Saudi Arabia with 200 qubits that will be deployed on the ground. This is a significant milestone as it corresponds to the first quantum processing unit acquired by a private company commercially owned. Also, a couple of weeks ago, we have installed Orion beta device in France in an HPC center. It's a 100-qubit QPU would be connected to a supercomputer at CEA in France. And there will be another one installed in Germany later in the fall. So those devices, they are quantum processing units coupled to supercomputing classical resources. And we really need to be working on how to better orchestrate the workflows between classical and quantum resources. And for that endeavor, we are partnering with IBM to be defining the interfaces, the standard ways to define classical quantum integration for quantum-centric supercomputers, to have it compatible for neutral atom technologies and superconducting qubit technologies. You can see here a few pictures of our installation of Orion beta device in France. We are very happy to have passed this milestone to be able to ship at the client's facilities a quantum processing unit and integrate this quantum processing unit with existing HPC infrastructures. So I've told you a little bit about our progress so far, what we've done, what has been our focus at Pasqal over the past few years, and where we are. And now let me spend a couple of more minutes to tell you about what's coming, what's next for the company in the next 5 years. We are really pushing engineering for neutral atoms QPUs. I've illustrated that in the first part of the presentation. We'll be using this strong mindset to boost performance of our QPUs, working on qubit scaling, addressability, the kinds of operations that you can do on the processors, also increasing the repetition rate of the processor. Quantum computers are notoriously slow. We need to tackle this problem hands-on. We've been also setting up an error-corrected quantum computing development track internal within Pasqal, working on error correction, gates, and interconnects. And this very ambitious R&D program will span over the next decade to provide quantum computer at scale for the industry. So of course, I've been focusing more about the hardware side of things, but we are also working on the software. What we want to do, ultimately, to increase the usage, increase the number of hours that are available for our clients and partners through the cloud. This is our mission in the next few years, and there will be several QPU generations enrolled in the next few years to achieve that. We've been developing a collaborative platform for our clients and partners to be able to get the grasp of our technology, use it, know our algorithm, and we will be enhancing this effort with learning contents, discovery contents, with the launch of a community platform later this year. We have decided to open source the higher level of our software stacks. We've taken a few steps on this direction already in the past with Pulsar, pulse-level quantum control software, Cadence, digital analog quantum software platform, and now we will be going one step further with the open sourcing of quantum routines, so the building blocks, the building block algorithms to implement on our QPUs, and they will be open sourced later this year, as well as our emulators. We really want to open up the ecosystem, open up the software stack so that people can make the best use of our hardware and develop this together. Just a short flash on our roadmap. So we're going strongly on technology and products. We've focusing on maximum number of qubits, addressability, range of operations, repetition rate. We've already made a few interesting developments in this area. I've showed you the 1,000 atom result today. We are delivering on this roadmap as 2024 advances. In terms of quantum processors, Orion Alpha is already there, available through Azure Quantum Cloud, and we have been shipping Orion Beta in HPC Center in France. Orion Gamma will be shipped in Saudi Aramco end of 2025. So with that, I'd like to thank you very much for your attention. Thank you.